Uh, yeah, thank you everyone for attending this session today. I'm going to present on my topic an IR-based QA system for impact of social determinants of health on COVID-19. Here are our problem statement, objective, and research question for this particular experiment. So our problem statement is to stem the exponential growth of infections from the recent COVID-19 pandemic. Researchers and many scientists have shown the urgent need for the multidisciplinary public health approach, incorporating rapidly evolving data related to social determinants of health and COVID-19. So our objective through this work is to develop an integrated architecture for a question and answering system that should be able to answer any questions related to impacts of social determinants of health and associated risk factors on transmission and outcomes of COVID-19. So our research question one is, can we develop a scalable architecture for the QA system, let's say Aqua, and can we evaluate Aqua by using standard evaluation metrics? Let's see if we can do it or not. So these are going to be the contents of my presentation for today. Let's start with why do we need AI technology? So there are large relevant corpus that is available over the web as of today. And the increased power to perform computations has enabled the application of artificial intelligence techniques like natural language processing, machine learning, etc., to process this huge data. So what is the domain which we are focusing on today? So it's SDoH, which stands for social determinants of health, which is also known as socio-economic conditions that might impact people's health. So studying about SDoH and how they impact impact crisis like COVID-19 can help decision makers or any person in that to that matter manage health emergencies so that everyone have equal opportunity to stay healthy. Recently, there is a CTV news article which stated like SDOHs are one of the important factors out of 5 big lessons learned from the pandemic. So let's go deeper into this. So we have used to build this question and answering system. We used NLP techniques. NLP is a field that deals with interaction between computers and human. Question and answering is a field of information retrieval and natural language processing. So the question and answering system allows the user to input the query in natural language. The question and answering system is available in two modes, two domains, which is open domain and closed domain. Open domain is something where you can search for anything, whereas closed domain only deals with some particular topic. So our experiment is a closed domain question and answering system, and the QA systems finds and returns relatively short and concrete answers to any given question. And the application of QA system is in various domains such as biomedical, tourism, sports, etc. And we have combined NLP with semantic web technologies because this combination can be used in any application where there is large unstructured data. So when it comes to unstructured data, like a natural language data is always an unstructured data. So to make this machine readable, we have followed two steps. One is to convert the unstructured data to structured data using NLP techniques, then linking this structured data to knowledge base like ontologies using semantic technologies. Therefore, we are bringing connection between unstructured data and formal data. So ontologies and RDF are considered as key semantic web technologies, and we have used these technologies in our experiment today. And ontologies are formally used to represent knowledge within a domain as a set of concept and the relation between them. So a set of concept and a relation between them is also known as triple. Each ontology class and relation may have an IRI associated with it, which is used to identify that particular class or a relationship, which is used as a unique identifier. So these IRIs can be used for various purposes, such as query generation and RDF annotation. RDF here stands for Resource Descriptive Framework, which is used for expressing the information across various applications and web. So RDF statements always follow this particular structure, which is shown here, which is subject, predicate, and object. Let's take an example from the figure shown here. So Bob, Alice are considered as two entities or two classes, and is a friend of is a relation between these two. So if we take this as a triple, Bob is a friend of Alice can be split into subject, predicate, object as shown here. And the corpus and ontologies merged. So we have used the CORD-19 corpus, which is released by Allen Institute of AI in collaboration with other institutions. They have considered the importance of COVID-19 and released this first version of COVID-19 open research dataset. And the ontologies we have merged to overcome the problem of domain coverage are CODO ontology, which is COVID-19 ontology, and pre-published we have merged this with pre-published ontologies like for homelessness and gender. We have also used PubMed articles as part of our corpus. And our fundamental process, like what is this all about? So when it comes to question and answering system, question can always be an online process, but answer has to be pre-processed and be stored in a database. So for that, let's take an example here as shown. Like individuals of low incomes are disproportionately likely to suffer from poor mental health. So when we break this particular sentence into smaller words or entities, using rule-based triple extraction, we get various words like this. These words has to be stored in Elasticsearch database for any query to find this answer when it is relevant to that particular query. So for this purpose, we need to maintain interoperability between these two processes. So to maintain that, we use ontology concepts like IRIs and map these IRIs to this particular words and store them in the Elasticsearch database. In the same way, we have a question here: who suffers from poor mental health? If we break that into triples, like we don't know who is it suffers from poor mental health. So this is the entities and relations that have been generated from question, and we generate Elasticsearch query out of these triples as shown here. And this query goes and hits the database to get the relevant answer when the URIs are matched with the answer URIs. So here comes our architecture. As you can see, like our motivation for this architecture is from means, a medical question and answering system combining both an NLP technologies and semantic web technologies. So our architecture have two processes basically, which is offline and which is online. Online, as I mentioned before, always works for questions, whereas offline is always done on answers. In our case, like we have text corpus, CORD-19 and PubMed. We have applied a few techniques on these to store them in Elasticsearch database, which I'll be discussing in detail in upcoming slides. So we have also have augmented ontology, as I've mentioned before. We have merged ontology, augmented it so that it fits our particular experiment, and then converted that to RDF format, and then processed it further. So first component of our architecture is rule-based triple extraction. So any document cannot be given to a machine, and machine cannot understand it as is. Therefore, we have to do some pre-processing steps, such as breaking the sentences or document into smaller words or entities or classes. So for that to happen, we have applied techniques like tokenization, part of speech tagging, dependency parsing, etc. Once the words are divided and they make sense and the relation between them makes sense, we created some patterns. Like for example, say here, for entity we have a noun followed by noun. Example, coronavirus vaccine. A noun followed by noun is an entity, and any relationship, maybe like suffering is an entity, like which is verb, can be considered as a relation between these entities. So altogether, we created patterns for entities and relationships through which we extracted triples. So we have extracted, like once we have given the corpus, we have extracted about 100,000 triples, in which few are valid triples, few are invalid triples. So valid because if you can see the row 361 here, low income suffer poor mental health. This particular statement makes sense. Whereas if you see the row 1191, there are special characters, numerical characters that have been involved in the triples, which doesn't make any sense. Therefore, these are invalid. We have overcome this invalid valid triple problem when in the next stage, which is linking. So linking is a process of mapping triple terms to the ontology terms. So this in this process, we used methods based on similarity. But other methods which can also help us perform linking method is like based on machine learning or based on graph. But we have not chosen this, but we have chosen the similarity methods, which are fuzzy matching and TF-IDF for our particular experiment. So if we can zoom in this linking architecture a little bit, it seems like this. So first, before doing anything, ontology in RDF format is indexed and stored in Elasticsearch database. Then ontologies in RDF format is input to similarity models, where the other input is from triples, that triples extracted using rule-based triple extraction in previous slide. So once we have these two terms study, similarity models evaluate if they are matching and meeting a threshold which we have provided. In our case, we have provided 90% threshold. And any triple term matching ontology term and the threshold is 90% and above, then the URI for that particular ontology term is fetched using in from the Elasticsearch database, mapped to the triple term and saved back in the Elasticsearch database. So for this particular in this particular thing, the similarity models we have used is TF-IDF and fuzzy matching, which I'll be discussing now. So TF-IDF stands for term frequency inverse document frequency. TF-IDF can be used to calculate the similarity between two records, considering the frequency of a word in a data or document. So say, for example, algorithm is a word repeated for about 10 times out of 1,000 words in a document, then the frequency of that particular term will become like the probability is calculated for that particular term, and that will become the frequency of that term. Next is fuzzy matching, which is a technique that helps in dealing with problems of knowledge representation in an environment of uncertainty, where we don't have ontology covering all the terms, or we don't have a semantic similarity models established. We can use fuzzy matching, which uses edit distance, also known as Levenstein distance, to calculate the similarity between two words. So this edit distance is calculated by giving a score for every replaced letter, a removed letter, and moving letter. So all these, like all the scores are given to each replaced letter, deleted letter, and the overall score is calculated. And indexing in Elasticsearch. So once we have linking done, we have rule-based done, now we have to store the data in the Elasticsearch database. For us to store in this Elasticsearch database need an indexed triples. For that, it uses again TF-IDF model, where it creates key to multi-value map, creating key value pairs, which is also known as inverted index, as shown here. This is forward indexing and this is the backward indexing. So this is how this inverted index is created, like terms become the index and document ID just becomes the maybe location of that particular word. And then this will be stored in Elasticsearch database, which will be easy for retrieval of any query answer related to query. So pre-processing such as normalization and stop word removal happen in this indexing process. Next component is answer search. So basically the search over RDF data is supported by two methods. One is a popular method, which is by using Sparkle queries. Another one is by leveraging information retrieval system using classical IR methods like indexing and retrieval. So again, Elasticsearch is an open source and one of the most popular search engines. It uses keyword search, and it used to optimize the search engine by adding weights of each keyword. In the example shard selection algorithm, if we take a word shard, is given more weightage because selection and algorithm are the words which occurs regularly. So the machine identifies that shard is the important one and it has to have high weightage based on the frequency of that particular term. And then it recognizes our search should mostly depend on shard. The weightage should be given to shard, but not selection and algorithm. So for this, Elasticsearch also have a powerful query language known as domain-specific language, which is mostly like filter context or query context. Filter context uses the exact match with the query, whether like all the given criteria is meeting or not. Query context is somewhere like relevant answers are also fetched. Why not Sparkle? When I mentioned here, like Sparkle is one of the traditional way of querying RDF data. Why are we not using it? So the reason behind it is Sparkle is not scalable on bigger data sets. So as I mentioned, we have about 100,000 triples extracted from 200 documents. If it exceeds more than millions or trillions of data, then Sparkle won't be as good as Elasticsearch is performing. So implementation with Sparkle is also not adaptable for other domains, because Sparkle mainly focuses on question types like when, where, what, how, etc. But if there is a complex question, Sparkle is not adaptable for such questions. So next component from our architecture is answer ranking. The final output from our system would always be the best ranked answer for this method. Elasticsearch uses TF-IDF scoring model again for this particular ranking. For example, if a term answer has two terms that matches the question terms with score 0.25 and 0.3, the rank would be sum of these two terms, which is 0.55. Once the rank for each answer retrieved is calculated, it is sorted in descending order, so that highest weighted sentence is always the best answer for a given question. So for enabling users to understand this process, we have provided a user interface where you can see like user can input their query in the search bar provided here and hit on submit, whereas it shows what query user has entered, what are the entities that are extracted from it, the URIs for the entities, and the top matching 10 answers are shown here. Like we also provided like a sentence, which is the answer for given question, and idea of that sentence, subject, predicate, object, like triples that matching this query, and the file from which this particular sentence has been extracted, so that if a user wants to know more on more about this data, they can just go to this file and fetch the answers. Also, we have displayed score here, so that user should know that this is the best score, this is the best match answer for this particular question. For this, we used Flask, which provides useful tools and features to create web application, as it is a lightweight Python web framework. For this purpose, Flask uses Jinja templates, which are used to dynamically build HTML pages, and it uses familiar Python concepts like variables, loops, lists, etc. And evaluation metrics. As our research question 2 goes, we have used system precision at K and mean average precision at K. K is the position of the answer. So we have used these two major metrics to evaluate and decide how many answers should be displayed on the user interface. And we also evaluated this particular experiment with recall and F measure metrics. So based on the results here, if you can see like system precision at K, it is grammatically falling till 7.5, but after that the curve is little flattened. Therefore, we have decided up to after top 10 answers, we are not going to display any answers on the user interface, which is not making any sense to the user, which is not related to the question user have. So we have decided to provide only 10 top 10 answers on the UI. So best example to understand this QA system is like Google search, where you just give an answer and it gives us, you know, top links, top matching links. So the QA system also works in a similar way. And our evaluation shows for top 5 answers, top 10 answers, top 15, and top 10, 20. And you can see from the results that after top 10, like even system precision, recall, and F measure have fallen drastically. Therefore, we have decided not to show top 15 and top 20 answers. Comparison of aqua to means, which is not presented in the paper, but I thought this would be a good for this presentation. So like as you can see here, these are all the components that enables question and answering system, whereas aqua has used minimum components, and means our motivation paper has used many components. Actually, means have published each component a separate paper and they have integrated all together. Their separate experiments were integrated all together, which took a lot of time. Whereas Aqua has essentially built from scratch with minimum components, and from the results we can see that Aqua is almost performing closely to means, and we believe more enhancement to Aqua can definitely outperform means. So our future works includes like we can improve the overall performance, as I mentioned before, by implementing some more enhancements to the works, like more semantic similarities, like cosine similarity for linking can be used so that more matching terminologies can be derived and saved in the database. Query expansion is a technique that provides alternative answers instead of no answers. Although our system is not providing no answers as of now, but the answers provided are not, some answers provided for few questions are not relevant. Therefore, we thought a query expansion method would overcome that drawback. So query expansion using ontologies, parent-child, sibling relationship will also improve the results. Building a trained model for each task, like named entity recognition and relation extraction instead of rule-based triple extraction, can enhance the performance of Aqua. The ontologies we created covers only homelessness, gender, and COVID-19 as of now. But social determinants of health factors are more beyond homelessness and gender. So if we try to create an ontology beyond homelessness, gender, for example, economic, education, other social factors, then this question and answer can cover a wide area of social determinants of health. And an appropriate axiom schema to further enhance the semantics of our search must be developed and integrated into our system. And our future works also include data cleaning. As I've mentioned, we have valid, invalid. So like we have got rid of invalid triples after implementation, but we can do this before implementation by doing some pre-processing on the document, which can be a future work. And also one of the major future work include getting this system evaluated by clinicians. So to conclude, with respect to our research question 1, we can assume in the affirmative that a scalable architecture of a QA system can be developed and implemented using technologies like semantic web, natural language processing, IR, to enable us to answer questions with respect to social determinants of health and its impacts on COVID-19. With respect to question 2, we use standard evaluation metrics like system precision, recall, F measure, and mean average precision to evaluate Aqua, and its performance is 60% at 10th position, like 10 top 10 answers for 20 questions we have evaluated this on. And it is expected that with the provided future works, like it would definitely enhance the performance of Aqua. And innovative aspects of this work include replacing traditional Sparkle query, which is not scalable, with Elasticsearch, and which is also used most widely in IR systems, and creating a domain-specific ontology which supports this QA system. The QA system which we have developed, the architecture is easily adaptable to any other domain, provided they have domain-specific patterns created for rule-based triple extraction, collecting domain-specific documents, and domain-specific knowledge graphs or ontologies. So this concludes my presentation. Thank you all again for attending this presentation today. I would love to answer if there are any questions anyone have.